After all these topics, we will cover up some exam questions. So for that exam question, these topics, discussion on these topics is necessary. Okay, so current is the change of charges per unit time. So your charges that will be equal to current times. So and your work done is the energy. Sorry, your volt is the energy per unit charge. Yeah, you can say that work done per unit charge.
Yeah.
So your work will be equal to V times del Q.
Yeah.
And your del Q will be equal to V times I del T.
Yeah.
So your work per unit time is, as we know, that is the energy, and that is equal to V times I. That is the power.
So P equals IV.
Yes. So your P is equal to IV. It means that if current and voltage is given to you, then you can find the power. And the unit of P is watt. And if V is equal to IR, so P will be equal to I square R. And if I is equal to V by R, then P is equal to V square by R. So it depends on the given data. Okay, it depends on the given data. Yeah. Okay. Now, okay, let's discuss on that how you will measure the resistance. So as we know that the resistance is the ratio of voltage and current. Okay. So and this graph, let's say this is the. So you can measure the voltage through using voltmeter and current through using ammeter. Do you studied about voltmeter and ammeter?
Yeah, that's easy. O level.
Okay, so and you will connect the voltmeter in series?
No, parallel.
Okay, and what will be the resistance of that voltmeter?
0.
0, good. Okay. Okay, I think you also studied about this, that if there is a zero resistance and there is some resistance, let's say that resistance is 0.01, okay, and if I connect a potential over here, then this is the current. You also studied about the KVL, KCL.
No.
Okay, so I1 and I2. This is.
Oh, I know. Kirchhoff's rule.
Yeah. So what? Let's say. What will be the value of I1?
What's the voltage?
Voltage is 5 volt.
Okay, so I divided by 0.101 equals what?
That is equal to 500. So I2 is 500. Good.
So if I2 is 500, then wait.
Let's say I3 is given to you, that is 3 ampere.
How can it be 3 amperes? It has to be greater than 500.
Sorry, that is 503.
Then so it will be 3.
It will be 3. No. If I said that it will be 503, then?
So 5, look. Oh my gosh. 500 will go to I2 and 3 will go to I1. Oh my god.
Okay, but if I say that, no, I1 will be equal to 503, then?
Oh. I thought you said I3, then why did you put it here? Look. Why did you write it here?
If I said that this I2 will be equal to 0 and I1 is equal to 503.
then I3 will also be 503.
Yeah, I3 is already 503. Then am I right? Am I right? You also studied about Kirchhoff current.
No, I2 cannot be 0 because there's a resistance of 0.01. So 500 amps must go here, and I1 will be 3 amps.
Okay, if there is an easy path, and if this path is easy and this path is difficult, okay, so on which path you will go? And you
Current will always go through the path with least resistance.
Yeah, current always flow the least resistive path. Okay, current always flow the least resistive path. But if the resistance is 0, then total current will flow through this path and will come out here.
Oh.
But if there is some resistance, let's say there is a minute amount of resistance that is 0.00001, then small amount of current will also flow in this resistance. But if the resistance is 0 in this part, then total all current will flow in this part.
But if the resistance is 0.001 here, what is the ratio of current then?
Then you will find the current through using the KCL. Or if you want to find this I3 current, then you need to find the parallel equivalent resistance of these two resistance, and voltage will be 5 volt. Okay, then from that you can find I3. I3 will be equal to V divided by R equivalent. R equivalent will be
I know that. But then how would you calculate I2? I2.
Okay, I2 you can calculate by using this method. That will be 500 ampere.
Oh, okay. Oh, so the exception is that if the path is 0 ohms, then there's an exception.
Yeah, there is an exception. That's good. Yeah, there is an exception when the resistance is 0, then the current will be equal to
0.
Then all current will flow across it. Okay. Some MCQs come such like from this topic, like resistance is given to you. Okay, huge amount of resistance.
I hate the MCQ questions are so hard. I hate it.
No, that is not so hard. If such like resistance is given to you, 3 resistance is given to you, and they ask you find the equivalent resistance. So mostly people get confused in this MCQ. So that will be, you will skip this resistance because least resistive path is given to you. You will skip this resistance. Your equivalent resistance will be equal to 2 ohm. Okay. Okay. Do you get it?
What?
Yes.
Tell me the values for the resistance.
The equivalent resistance of this RAB will be equal to 2 ohm.
I don't understand what you drew. Can you draw it again? Wait, clear the book.
Okay, let's say this diagram is given to you, and this terminal is A terminal and this terminal is the B terminal, and each resistance have 1 ohm, and the question is find RAB. So
what is this line here?
This is the conductor.
This is confusing. I don't understand.
Okay, so electron will start traveling. Okay, will start from this terminal. Electron will flow because there is no other path, so electron will cross this resistance. So resistance will be 1 ohm. Then when electron comes out,
the answer is 3.
Yes, the answer is 3. Okay. Then electron will flow like this, then it will come over here, then it will go like this, then it will come over here, and the total resistance is 3 ohm.
Oh, I got it.
Yeah. Okay, so let's come toward that topic, measurement of resistance. So according to you, I will connect the voltmeter in parallel to this resistance. And according to you, the resistance of this voltmeter will be equal to 0. And what about the resistance of ammeter?
0.
Okay, that is also equal to 0 ohm. So electron will carry the energy, will get the energy from the battery and will move toward like this. So from here, electron will move toward like this. Okay, and when electron reach over here, there is a least resistive path. Okay, so electron will flow will follow this path and will move like this, and it will come over here and it will get back to the battery. So the current skip this path. So, and you are going to measure the resistance. So what you will do? You need.
Yeah. So what will you do?
So what you will do is you keep the resistance 0. As you said that the resistance of this voltmeter will be equal to 0.
You can use a voltmeter with 0.1 ohms.
Okay, if you make it 0.1 ohm, then small amount of current will flow over this because this resistance is higher. This resistance may be 5 ohm, yeah, 6 ohm. 5 or 6 ohm is greater than 0.1 ohm.
Oh.
So as V is equal to IR, so if resistance is high, as current have an inverse relation with resistance. If resistance is high, then it means the current is minimum. So minimum current will flow in this path, and large current will flow in this path, and maybe it will damage my voltmeter.
Oh my gosh! But I don't know.
Yeah, as Farjana is going to make the resistance 0 or near to resistance, so that is not good. You are damaging my voltmeter.
Oh my god! Then how do voltmeters work? I always use voltmeter.
Yeah. If I am standing over here, okay, then I will make this resistance infinity.
Oh.
So that no electron will try to come on this path. All electron will move over here, and so I will have high current on this path. Because if resistance is infinity, then the current on this path will be equal to 0. So the current on this path will be equal to 0. So I will get a true value of resistance, okay? Because all current of this battery is flowing in this resistance. So resistance is equal to voltmeter divided by current. So all current will flow across this resistance, and I can measure the potential difference across this resistance.
Oh.
Because here it will have a high potential, and here I will get a low potential. But that will only be possible in theoretical that is possible if I can make the resistance infinity. In practically, it is not possible to make your resistance infinity.
Yeah, just a great number like 1000 ohms.
Yeah, 1000 ohms. I will make it as huge as possible.
What about ammeter? Ammeter is 0 ohms, right?
Yeah, ammeter will have a 0 ohm because if there is some resistance, then some potential drop will also occur in this ammeter, and that will also damage the.
And that will affect the current. That will affect the measurement of the current being.
Yeah, that will also affect the current, and that will not give me the exact value of resistance because this resistance will have, and some sort of error will also be present in this circuit. Then.
Oh, I get it.
Okay, so. Okay, so now there is another term that is the. Okay, so the graph of, if this graph is given to you, okay, and this is the graph. So the gradient of this graph will give you the inverse of resistance.
Yeah. V is independent.
Yeah, V is, yeah, that is independent. I told you last time. Okay. So this is the first part, okay? The graph, if there is a graph between current and voltage, then the gradient will give you 1 by R value, okay? Inverse of resistance. Second point is that for ohmic conductor, your voltage will be equal to IR. And for each conductor, this resistance will have a fixed value.
Yeah.
It means that this value, resistance, depend on the device, that which device you are using, okay? So for ohmic conductor, this resistance will remain fixed. And then if you increase the voltage, then the current will get increased. And the third point is, in metallic conductor, resistance remain constant. This resistance remain constant in metallic conductor if there is some condition. If physical condition, yeah, physical condition, you can say physical. Temperature, pressure, okay, so that is the physical. Physical condition remain constant.
What's the difference between 0.2 and 0.3?
Okay, if your material is, if you have only one material, okay, then the value of that resistance, will remain constant for that material. Yeah. But if there is some sort of variation in temperature and pressure, then the value of that resistance of that material will get changed. So you need to keep both conditions. Like if this resistance is constant at 25 degree, temperature will also given to you. 25 degree and pressure will also given to you.
Yeah.
Yeah, if you are using some like copper, okay, so they will give you the resistance value of copper. That will be very small amount of resistance because copper is the good conductor. And also along with this resistance, this fixed value resistance, temperature will also be given to you at this temperature and at this pressure. Okay, now let's come toward the.
What if two conductors were mixed? So, for example, two metallic wires of different materials were mixed together. Would it still follow the Ohmic law?
Okay, wait. And on transmission line, we use ACSR conductor.
Yeah.
That is the aluminum conductor steel reinforced. Steel is not a good conductor, but it will strengthen the conductor.
Oh yeah.
Aluminum is not as good conductor as copper, but we use this aluminum conductor on transmission line.
Because
it's
I don't know, because it's cheap.
Because it's cheap. Good.
I thought aluminum is expensive.
Yeah. No, aluminum is cheaper than copper. Copper is expensive.
Oh, okay, aluminum is expensive, but compared to copper, it's cheap.
Yeah, compared to copper, it's cheap. And
because when I go out to buy aluminum for my cooking, it's expensive.
Okay, yeah, that is expensive. Okay, so aluminum is and what about the weight?
It's light, very light.
Yeah, it's light, so that's why we use this for the transmission. Okay, so on transmission, in transmission conductor, if you go through the transmission conductor, then transmission conductor has central steel conductor. That is the steel. Okay, this is steel.
Yeah.
And on steel, we have lots of aluminum conductor.
Yeah.
Okay, so this is the mixture of the conductor, mixture of aluminum and steel. Okay, so this steel give the strength. Okay, this steel give the strength to this conductor, this transmission line, and this aluminum conductor will is a good conductor of electricity. So electricity will flow through this conductor.
Yeah.
So this conductor is known as ACSR. So on transmission line we use this conductor ACSR.
Yeah. So what's the conclusion here?
No, you told me that if we use the mixture, so we use mixture where there is some sort of need, like if we need strength.
Yeah, but I'm saying if we use mixture, does it still follow V equals IR? Ohmic law. Does it satisfy this Ohmic law?
It satisfies. No, in this, okay, so in this case, there is a least ratio path, and that is the aluminum.
Oh.
So current will flow on in aluminum conductor. So that will follow this path.
Oh.
That is the Ohmic. And
but if the wire was like this, and it's mixed together with the steel, then will it follow the Ohmic law? No, right? Because, for example, mixture of aluminum and copper wire.
That will not follow the Ohmic, because this conductor will store the energy.
Okay.
Because this is the inductor, that is known as inductor. Inductor is a storage element. It will store.
Okay, fine. That's electrical engineering, please.
Okay, so now let's come to another topic. On conductor, okay, one question which also come into your mind, that why we are covering this steel conductor. On the surface of steel conductor, we put aluminum conductor. So that is actually in conductor, mostly in AC conductor. If you want to flow the alternating current on this conductor, then majority of electrons flowing on the surface. Okay. Yeah. Less amount of electron will flow at the center.
Because that's where the steel is, right?
Yeah. So that's why we put a steel over here, and that will give us a strength. Okay. So there is a huge story behind this, that why majority of electron is flowing in this, but that is not at your level. That is beyond your level. Okay. Now let's come toward the resistivity.
It's the property of a material that determines.
Okay, and what will be the formula of this resistivity?
Wait, what's the definition? Resistivity. Wait, can you send me all these slides? Don't delete everything. Go to the next slide.
So how I will send these slides?
It's easy. On Zoom, everything is saved.
Yeah, there is also a sign of new slides like this. So there are two slides. Last one slide is this, and this is the new slide. But I erased all the working which I did over here. So
Okay.
okay,
Definition.
but it's how you will save these slides over here.
It's fine. Leave it.
Okay, so resistivity. Resistivity is the, according to Fajana, resistivity is the property of the material. Yeah, that's good. If this conductor is given to you, okay, and length of this conductor is, let's say, L, and the area of this conductor is, let's say, A.
Yeah.
Then your resistance will be directly proportional to L, and your resistance will be have an inverse relation with area. It means that if you increase the length of this wire, then it will increase your resistance. And it will, if you decrease the area of this wire, then it will increase the resistance.
Yeah.
You can understand this concept like this. If this is the path of your, if this is the path, okay, and you want to move from A point to B point, okay, and let's say there are some, what you can say.
Yeah, I know. Obviously, if the area is big,
yeah, okay, so you got it. Okay, so if the area is big, then electron can easily pass there. Then sorry.
But what about length? Why does length increase as resistance increases?
Yeah, so that's why. Let me draw it.
I understand area, but not length. No, but explain it in terms of electrons. I'm not a baby.
Okay, so if you want to move from A to B, okay, so it will be easier for you, or no?
Oh yeah.
As compared to this, it will be.
Yeah.
Here, yeah, this will be easier because the length of the wire is less.
More.
Yeah, so less length, so it means less resistance. But if you increase the length, so it means you are increasing the resistance. Same resistance will get increased. Or maybe at some point there is a huge resistance, or at other point there is a less resistance.
But if in the exam they ask why does resistance increase with length, what do I say? Because as the length increases, there's more metallic ions for collision with the electron.
No, you will say that every conductor have some resistance. Okay. So if you increase the length of the wire, then you will increase that resistance.
Oh, okay.
Okay, so on each wire, resistance is given to you. That is like 2 ohm per kilometer. This sheet will given to you, and on that sheet, this will written 2 ohm per kilometer. So if you want to buy 6 kilometer wire, then you can find resistance from this. That will be 12 ohm. For 6 kilometer, resistance will be 12 ohm.
Yeah.
Okay, so this data will be given to you. For each wire, this data will be given to you. Okay, so resistance is directly proportional to L, and resistance is inversely proportional to L, A. So total your resistance will be directly proportional to L divided by A. Okay, and your resistance will be equal to rho L divided by A, where rho is the resistivity. Okay, and the unit of this resistivity is ohm meter. That is the SI unit.
Yeah.
Okay, and resistivity is the material property. Okay.
Wait, is it ohms per meter like this?
Ohm meter, not per meter.
Okay.
Yeah. Okay. So now, okay, how you will find the resistivity? Okay. So how you will find the resistivity? So let's first of resistivity. If you rearrange this equation, your resistivity will be equal to RA divided by L. Okay. So let's find the area. Okay, I am going toward the next. Okay.
Yeah, I know. I know how to do substitution. If you give me the values, I know how to rearrange. That's easy.
Yeah, that's easy. Okay, wait. So your resistivity will be equal to RA divided by L. Okay. Yes, here is okay. So first we are going to find the resistivity value of this conductor. Okay, so first of all we need to find the area. So your area will be equal to pi r square, and that will be equal to pi d square divided by 4. So if the wire is uniform, then you will have only one d value, and you put that value, and from that you will get area. But if your wire is not a uniform, then what you will do? Then your diameter will not be same. Then what you will do? You will take diameter at different points, and then you will find the mean of that all these diameter. So you will take the mean of that diameter. Okay, so putting that value over here, so you will get area.
Yeah.
Okay, and along with this wire, one graph will be given to you, and that is the resistance length graph. Okay, that will be like this. Okay, so if it depends on your length of your wire. If your wire is 6 kilometer, so at 6 kilometer your resistance will be this. So this point will give you R by L value. Okay, so let's say that is 6. So your R by L value will be 6 times area you can get from here. So through this you can find the resistivity of this material. If resistivity is not given to you, then you can find that resistivity through this method. Okay.
Yeah.
Now let's come toward the last topic.
You plot resistance against change in length, then you calculate the gradient, and then times that by the area.
Yeah. Now let's come toward the last topic, which is your favorite topic, and that is the superconductivity.
Yay. I hope we're covering everything in the book, because in the book there's so many little things that we need to know. Like it comes in the exam. I don't know.
Yeah. Yeah. So after covering electricity chapters, so we will do questions. Okay, and hopefully that question will be easy for you if you get all these concepts. Okay.
Yeah.
And your exam will be
in 4 weeks.
Okay, in 4 weeks.
Actually, in first week of June.
And that will be online?
Yeah, and my teacher is going to monitor me.
Monitor me?
Monitor.
Okay, monitor, okay. And your teacher is basically from UK?
Yeah, my school teacher.
Okay.
My teacher is going to monitor everyone, all the students, not only me.
During exam?
Yeah, so annoying. I want to text you for the answers.
Yeah, actually, a few days ago, my one student had exam, and that is online, and she is too much happy. She said that, sir, why not all exam is like this? If you are sitting in front of me, and you will solve my exam, because I solved most of the questions for her in her exam. So that's why she was too happy. That
Wow.
it will be good if it will be good if all exam is like this online.
Yeah.
Because her teacher sent exam at 9:30, and exam end up at 11 a.m. But her teacher said that you can upload it up to 2 p.m. So I, along with her, I get online at 9 a.m. and we solved that all questions through group discussion.
That's so bad.
Yeah, but actually, her mother told me that helped her in her exam. So that's why she is in 7th class, grade 7. So that's why. And she is a bit weak. So that's why her mother told me that help her in exam. So that's why I helped her.
Yeah.
Okay, so superconductivity is the superconductivity. A superconductivity is a wire or a device made up of material that has zero resistivity at or below a critical temperature. If this graph is given,
what does that mean? What does that mean?
If this is the temperature, okay, and that is in Kelvin, and this is the resistivity.
Yeah.
Okay, so if you increase the resistance, then if you increase the temperature, then your resistance will get increased like this. Okay.
Yeah.
And let's say this is the critical temperature of this material.
What does critical temperature mean?
Critical temperature is the that temperature at which your resistance, your resistivity is equal to 0.
Oh.
And this temperature is different. This is the material property. You can say that this is the material property. It is different for different conductors.
Isn't it very low, like minus 500 degrees Celsius, minus 200 Kelvin?
Yeah, it will be low because that's why we are going to measure it in Kelvin.
How do we?
But it depends on the material. Which material you are using. If you are using copper, okay, then if you are using copper, then the superconductivity value of this copper is 1.7 times 10 to the power minus 8.
Kelvins.
No. This is the superconductivity.
What does that mean?
That means that your resistance will get superconductivity. It means that you have. I think it means that below critical temperature, your resistivity will be equal to this.
Oh, okay.
And for PVC, which is a good insulator, the value is 10 to the power 14. About 10 to the power.
High resistance.
Yeah, that has a huge resistance. So, this is the critical. So if you decrease this, so if you decrease the temperature, okay, then the resistivity will also decrease like this.
Yeah.
Okay, and at critical temperature, the resistivity will become 0. Yeah, will become minimum. And ideally, we are talking about that the resistivity will become 0. And your resistivity is equal to resistance times A divided by L. So it means your resistance is equal to 0 below the critical temperature or at the critical temperature.
Isn't the resistance maximum? Yeah.
And this decrease of this 0 resistance is the property of the material. It depends on the material. For other material, it will be like this, or it will be like this. So this will be the critical temperature for that material. For 1, this will be critical temperature for material 2. This will be critical temperature for material 3.
It must be very expensive to find superconductors because not many materials have this property.
Okay, so when
right?
you so what you say?
Not many materials have this property.
No, all materials have this property.
But that means you need to freeze it. You need to put the wire in the freezer.
Yeah. No, that is not necessary. You put all the wire in the freezer.
Otherwise, how can it reach the critical temperature?
If you see over here, the superconductivity of copper is 1.7 times 10 to the power minus 8. So that is the good conductor, okay? And the resistance value is near to 0. But in PVC, that is the high conductor, about 10 to the power 14. And superconductivity is high for PVC. So your resistance, maybe that will be because if you look at this graph, then if this is the current and this is the voltage, okay?
Yeah.
Then your voltage and current graph is like this, and this is minus 273.
Yeah.
So if you decrease the temperature, then the current will get. So if you freeze it, then the current will be equal to 0. But at room temperature, let's say this is the 25 degree, and there is some sort of. Okay, leave it. We will make a huge discussion tomorrow on this topic. Okay.
Okay.
Okay. So if resistance is 0, so if resistance is equal to 0, then it means that your current is also equal to 0. Then it will have no heating effect. It means that there is no potential difference. And
how do you ensure the critical temperature is reached? You have to put some special material, some special equipment.
You will decrease the temperature, okay, and measure the resistivity at some specific temperature.
Okay, fine.
Okay, and critical temperature of all material will also be given to you. that if you are this material, then critical temperature is this. Then you will understand that at this temperature or below this temperature, my resistance will be equal to 0. So if you are using this material in different application, then you will make sure that you have this temperature, critical temperature.
Okay.
Okay, so the application is we use this superconductive material in high power electromagnetic that will generate a very strong magnetic field in devices such as MRI. In MRI, we have a huge magnetic field. If you go to the hospital, there is an MRI machine. Okay, and here patient is laying over here, and okay. Oh.
God, is that? You're good at drawing.
Yeah, I am engineer, so that's why. Okay.
I was.
Okay, so this is the let's say this is the patient. Okay.
Yeah.
And this huge is the magnets. Okay.
Yeah.
And we examine the different parts inside this patient through using this these magnetic fields. Okay. And this is the MRI. If you go to the hospital, you will watch this MRI. Okay. So in MRI, we need a strong magnetic field. So either we generate that strong magnetic field through using these huge magnets or using this superconductor material. Or we can also use this superconductor material in particle accelerator. Okay. If you want to accelerate the particle, then you will use superconductivity. There you use this material, superconductor material. Okay, so we also use this.
Wait, where's the superconductors in this MRI scanner?
So you can use the here we use the magnets. Okay, these are the magnets.
Yeah.
So here you can use the superconductor material instead of this magnet. That will generate the strong magnetic field.
How?
Because there the resistance is equal to 0. So when the resistance is equal to 0, then it means that there is no loss of electrical power or there is no heating effect. If there is no heating effect, then it means that there is no loss of power.
How? Yeah. So
So
how does magnetism? How does that generate a magnetic field?
So if electrons start motion, then they will have a magnetic field.
Oh yeah.
So there is no loss of energy.
Why can't they use normal conductors without zero resistance? Oh, is it to do with efficiency? Because of efficiency?
Yeah, it's impossible to make sure that the resistance of your conductor is equal to 0.
But it's fine. It's fine if the resistance is high. Why does it always have to be 0?
It's fine if the resistance is high. Okay, if you have this conductor, you buy this conductor, and the shopkeepers say that the resistance of this material is 60 ohm per centimeter. So Farjana will tell him that okay, fine. So if you put power like 60 watt, then all power will drop over here because it will lose in the form of heat. So that's why it's not fine. Okay, and we also use this superconductor material in electric motor. Okay, in electric motor, the weight of the electric motor is high because of using high weighted magnets. Okay, so superconductor through superconductor we can generate a high magnetic field, and that will give us a lightweight electric motor. And we also use this superconductor material in power cables that transfer or electrical energy without any energy dissipation. Okay.
Yeah, that's why aluminium is used, because aluminium is a superconductor.
And aluminum also has some resistance.
Oh.
That is greater than cooldown. That is greater than the resistance of the copper. And normally we use the aluminum on transmission line. We use the aluminum. Okay. And if you want to make the resistance equal to 0, then you should keep the temperature less than the critical temperature of the aluminum. Okay, and that is impossible in outside environment.
But it says on internet examples of superconductors include aluminum.
Yeah, that is aluminum. But if you place that in such a condition that the temperature of the surrounding of the aluminum wire is less than the critical temperature or equal to critical temperature, then your resistance will be equal to 0 for aluminum as well. Okay, so now here it's assembly time. That is 3:21 a.m. Okay, so I am going to Salary. If you have any question, you can ask.
Okay, oh my gosh. So you know the scanner, is it very cold? Because it needs to maintain the critical temperature.
Okay, ask again.
Is, you know, the MRI scanner, is it very cold?
No, it's not very cold. Okay, wait, I will show the MRI.
Is it slightly cold to ensure that?
It's not cold. If you use the superconductor material and if you use the superconductor material in MRI, then you need to make sure that the temperature of that surrounding is less. But you will use that material. You will use that material which have the. If in MRI you are going to use the. If in MRI you are going to use the superconductor, then the material should have a critical temperature that is equal to 25, that is equal to 30 degree. And I think that is not present. There is no such type of material.
Yeah, exactly. It's impossible.
Yeah, it's simple. So that's why we are going to use this huge magnet. These are the magnets. And maybe in next chapter we will do a detailed discussion on this. That how MRI. What is the physics behind this MRI?
It's impossible to get a superconductor for MRI. So what do we do? Do we use normal conductors?
Yeah, we are using normal conductors. So that's why the conductor is huge. And we are also using normal conductor in electric motor.
Then why did you say that the superconductor is an example of electric motor? And
that is just the application that you can use the superconductor material in MRI, but you need to fulfill the condition of the superconductor material. But that is impossible in our daily life. So that's why we are going to use this whole huge magnets. Okay.
So what's the real life?